We will start off our discussion of the chemistry of life with the periodic table. This organized table of elements consists of columns, referred to as groups, and rows, referred to as periods. Let's examine one of the elements, lithium, in closer detail. Lithium is a soft, silvery white metal as represented here. If we continuously break down this block of lithium into smaller and smaller pieces, the smallest particle that will retain all its chemical properties is known as an atom. The structure of the lithium atom is presented here. The atom consists of three subatomic particles: protons, neutrons, and electrons. Notice the neutrons and protons are located in the nucleus. The proton has a positive 1 charge and mass of 1 atomic mass unit, or AMU for short. AMU is another unit used to measure mass. The neutron is neutral and has a mass of 1 AMU. Electrons are located in the electron shells that circumscribe the atomic nucleus. An electron has a charge of -1 and negligible mass. The lithium atom has 3 protons, 3 neutrons, and 3 electrons. The electrostatic attraction between the negatively charged electrons and positively charged proton holds the atom together. The lithium atom has 2 electron shells. The first electron shell is closer to the nucleus, while the second electron shell is farther away. Electrons can transition from the first electron shell to the second electron shell. Because electrons are attracted to the positively charged nucleus, it takes absorption of energy to push the electron from the first to the second electron shell. When electrons drop from the second to the first electron shell, energy is released. So far, we have discussed the structure of the lithium atom. Let's see how to represent this atom in symbolic form. The shorthand symbol for lithium is Li. The left subscript indicates the number of protons, which is referred to as the atomic number. Keep in mind the number of protons determines the element the atom represents. If you refer back to the periodic table, notice that each element has a different number of protons. For instance, oxygen has 8 protons, and neon has 10 protons. Now let's return to our lithium symbol. The left superscript indicates the number of protons plus neutrons. This value is referred to as the mass number. Sometimes an atom can be represented by the full name of its element, followed by a hyphen and its mass number. The last term that we will discuss is atomic mass. If we decide to put a lithium-6 atom on a scale, the scale would tell us the atomic mass, or the mass of the whole atom. The atomic mass of lithium-6 is 6.015122 AMU. This value is closely approximated by the mass number because the main contributors of mass are neutrons and protons. Electrons have negligible mass. Let's think about 2 possible situations. If we added a proton to a lithium-6 atom, it would become beryllium-7. The addition of a proton changes the element and increases the mass number by 1. If we added a neutron to lithium-6, it would become lithium-7. Notice the element does not change and only the mass number increases by 1. Now let's focus our attention to the lithium-6 atoms only. Atoms with the same number of protons but different number of neutrons are called isotopes. Lithium has multiple isotopes, including lithium-6, lithium-7, lithium-8, lithium-9, and much more. Below each isotope, we have tabulated the number of protons and neutrons. Isotopes can be further classified as either stable or radioactive. Radioactive isotopes emit particles and energy, whereas stable isotopes do not. The process of emitting particles and energy is known as radioactive decay. Let's take a close look at this periodic table. We will focus our attention on main group elements, which are colored blue, and ignore the transition metals, which are colored gray. To simplify things, we will cut out the transition metals to create a truncated version of the periodic table. Each of the atoms in the first row of the periodic table have one electron shell. Atoms of the second and third rows have 2 and 3 electron shells, respectively. Although atoms can have multiple electron shells, the outermost shell, also known as the valence shell, is the most important. We have color-coded the valence shell as blue circles. There are 2 atoms in the first row, hydrogen and helium. Hydrogen has 1 electron in its shell. As we move from left to right across this row, electrons are added one by one. Helium has an additional electron. Thus, it contains 2 electrons in the first shell. It is important to note that the first shell contains a maximum of 2 electrons. The electrons in the outermost shell are referred to as valence electrons. Atoms of the second row have a total of 2 electron shells. The first electron shell is occupied by 2 electrons. Lithium starts off the second row and has 1 electron in the valence shell. As you move from left to right, we continue to add additional electrons. Beryllium has 2 valence electrons, boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, and neon has 8. The second shell and all the shells after the shell can hold a maximum of 8 electrons. Atoms of the third row have a total of 3 electron shells. The first 2 shells are completely occupied. Sodium starts off the third row and has 1 electron in its valence shell. Moving from left to right, magnesium has 2 valence electrons, aluminum has 3, silicon has 4, phosphorus has 5, sulfur has 6, chlorine has 7, and argon has 8. Again, the third shell can hold a maximum of 8 electrons. The periodic table can be categorized as atoms with an unfilled valence shell and atoms with a filled valence shell. Atoms with an unfilled valence shell are unstable and undergo chemical reactions, whereas atoms with a filled valence shell are stable and do not participate in chemical reactions. Before we discuss chemical bonds, we need to discuss an important chemical property, electronegativity. Electronegativity is the measure of an atom's affinity for electrons. Elements with high electronegativity accept electrons. Fluorine is an example of an element with very high electronegativity. Thus, it freely accepts electrons. Elements with low electronegativity donate electrons. Sodium is an example of an element with low electronegativity. Thus, it freely donates electrons. Elements on the left side of the periodic table have low electronegativity, and elements on the right side have high electronegativity. Let's move on to discuss chemical bonds. There is a spectrum of possible chemical bonds: nonpolar covalent bonds, polar covalent bonds, and ionic bonds. Nonpolar covalent bonds form between atoms of no or little difference in electronegativity. For example, the bond between two fluorine atoms, or the bond between a carbon and hydrogen atom. Keep in mind that each bond contains 2 electrons. Because the electronegativity is the same for both fluorine atoms, the electrons will be shared equally in the middle. The small difference in electronegativity between carbon and hydrogen also means the electrons will be shared equally in the middle. Polar covalent bonds form between atoms of moderate difference in electronegativity. For example, the bond between an oxygen and a hydrogen atom. Because oxygen's electronegativity is greater than that of hydrogen, electrons will be drawn closer to the oxygen. We signify this with an arrow directed toward the oxygen and a tick mark at the hydrogen. Because of unequal sharing of electrons, the oxygen is partially negative, denoted by a delta negative sign, and the hydrogen is partially positive, denoted by a delta positive sign. Ionic bonds form between atoms of large electronegativity difference. For example, the bond between sodium and chlorine. The electronegativity values have a very large difference. For this reason, electrons are not shared, but transferred from the atom with low electronegativity to the atom of high electronegativity. Here, the electron is transferred from sodium to chlorine. This results in the formation of 2 ions, a positively charged sodium ion and a negatively charged chloride ion. An ion that is positively charged is a cation, and an ion that is negatively charged is an anion. In summary, there are 3 possible bonds. In nonpolar covalent bonds, electrons are shared equally between atoms. In polar covalent bonds, electrons are shared unequally and results in partial positive and partial negative charges. And in ionic bonds, electrons are transferred from one atom to the other. The structure of a water molecule is presented here. Recall that oxygen has greater electronegativity than hydrogen. For this reason, the pairs of shared electrons in the polar covalent bonds are closer to the oxygen. This results in a partial negative charge for oxygen and partial positive charges for the hydrogen atoms. Water is a polar molecule because of the presence of positive and negative charges. Let's add another water molecule to this picture. Notice the positively charged hydrogen of one water molecule forms a bond with the negatively charged oxygen of another water molecule. This bond is referred to as a hydrogen bond. Hydrogen bonds are considered intermolecular bonds because it forms between two water molecules. This type of bond is different from the intramolecular bonds that are holding the atoms of the water molecule together. To reiterate, intermolecular bonds form between two molecules, whereas intramolecular bonds form between atoms of one molecule.